So, question 1 gives us a definition of a jump discontinuity. And algebraically, or really kind of intuitively, we can think of a jump discontinuity as we've got some piece of graph that's going to a point, and then it jumps to another piece of graph. Now, I'm just drawing an example of that. It can look different than this, but there's essentially a jump in the graph itself at a particular value. So, the definition in calculus says that the limit from the left exists, the limit from the right exists, but they're not the same as one another. All right? So we can see that this is going to a different y value than this would be. Okay, so it gives us this function, and we have to show that it has a jump discontinuity at 5 by finding the limits, and they will be two distinctly different values since it has a jump discontinuity. So we want to find the limit as we approach 5 from the left. All right, so we need to go up here and see which of these conditions on the right are x values that are to the left of 5 or that are less than 5. So x is less than 5 means we're going to use this piece right here. We're going to plug a 5 into that piece to get the limit. And in this case, 25 minus 5, this is going to be 20. So the limit from the left is 20. To get the limit from the right, we need values that are bigger than 5, or to the right of 5. That's x is greater than 5. So we're going to plug in to this piece. 4 over 5 plus 8. And that's 4/13. I apologize for my bad handwriting on here. I am trying to write with a mouse. Okay, so let's go to number 2. We want to evaluate these limits, and we're going to enter infinity or negative infinity using 2 zeros apparently to get our infinity and negative infinity. Now, we want to find the limit as we approach 9/2 from the right of this function. If we try to plug 9/2 into the bottom here, it's going to give us 0 in the denominator. So we can't do that. There are 2 ways that we can find this limit. One of them is to graph the function, and the other one is to plot some values that are to the right of 9/2, but are very close to 9/2, and we'll get closer and closer. And really, 2 values is enough for us to see whether this is going to infinity or negative infinity. So 9/2, if you put it into your calculator, is really 4.5. So I'm going to choose something to the right of 4.5, slightly bigger than 4.5, and plug it into this. 4.6, for example. So let's plug 4.6 into our function and see what we get. And again, I apologize for my first grader-like handwriting on the screen. I'm going to put this into my calculator and see what I get. Now, this gives me negative 805. Now, that's a pretty large negative, so it would appear that it's going into negative infinity. But let's get just a little bit closer to 4.5, and if it goes big or negative, we'll know that it's going to negative infinity. So if I get closer than 4.6 to 4.5, let's say 4.55. So again, if I go 35 times 4.55 and let my calculator do this, this gives me negative 1592.5. So it's definitely getting bigger in a negative direction. So this limit is going to negative infinity. Now, I said that I'd show you graphically how to do it, but let's do this one first, and then we'll go to how to graphically find these answers as well. You might find doing the graph is easier than plugging in like this. All right, so Now we're going to approach 9/2 or 4.5 from the left side. So we want things that are smaller than 4.5 but close. 4.4 is really close, so I'll put 4.4 into our function. I'll go over here, just room-wise on here. It's difficult. And I'll let my calculator do this. And I know that looks like a 9, but it is 4.4. So in this instance, I get 770. That's pretty large positive. It would appear to be going into positive infinity, but let's do one more to make sure. So if I get a little bit closer to 4.5 than 4.4, I could do 4.45. So if I stick that in, and let my calculator do the work here, I get 1557.5. So notice it's getting bigger in the positive direction, so we can tell that it's going upward, so we would expect this one to be infinity. Now, I want to show you graphically how we can do this, and there's a nice program called Desmos. So I'm going to go to desmos.com. So I've gone to desmos.com and into their calculator, and I have typed in our function. And what we see over here is really just part of the function. Notice we can only see 9/2 is somewhere over here, and right now you can only see part of the function. So what I'm going to do first of all is move the screen so you can see a little bit more. Still can't see anything near 9/2. I'm probably going to need to change my window. So we'll click this little wrench over here, and the y-axis probably needs to change so I can see more of the graph of this. So I'm going to change it to -20 and +20 and see what that does to help me see more of the graph. I'm still only seeing part of the graph, so let's go bigger, go -100. And now I see the right-hand side of that graph popping up in +100. And now that I can see that, let's notice that 9/2 is right in here. And as I come at 9/2 from the left, this is going up forever. And as I come at 9/2 from the right, this is going down forever, which corresponds with the answers we got back here. When we come at 9/2 from the right, it's going down forever. When we come at 9/2 from the left, it's going up forever. So you can do this either way, by graphing it and looking at the graph, or plotting some points that are close and determining in which direction they are going. All right, now let's look at question 3. And there we go. All right, so the most common way we're going to do some of these is by looking at a graph and determining from the graph what their values are. All right, so the first thing is asking us to find f of 8. So we want to go to an x value of 8 and see what the point is. So if we go up, the y value appears to be at 5. Now, it does appear like it could be slightly off, and hopefully, though, they mean for that to be a whole number. All right, now, x approaches 2 from the left. So here's 2. If we approach it from the left of 2, so we come toward it from its left, it goes to a y value of 2. If we, oh, I'm sorry, that's a different one. X approaches 8 from the right. So let's go to 8. Here's 8, and here's its corresponding y value. If we approach that from the right side of it, it is going toward 5. And now the limit as x approaches 7. Now let's notice this is neither right nor left. This is both sides. So let's go to the 7. Notice there's no point here, but if we approach 7 from the left of it, it's going towards 6. If we approach 7 from the right of it, it's again going towards 6. The limit is 6. So remember, the limit is what it tends to go toward. It doesn't actually have to have a point there. All right, and I think I can probably do one more on this video. So let's go down to number 4. Very similar. Okay. So as I look at number 4, I realize that this is not what I intended here when I assigned it. So I'm going to tell people this one's extra credit. Don't worry about number 4. It really belongs in our derivative section, so we'll leave that for now. Let's go down though, and we'll grab number 5, and we'll see there's others that are like number 5. Now this randomly generates numbers, and so sometimes there'll be a number here. This time it randomly generated a 0. But let's notice we're doing the limit as x approaches 0. If we just plug 0 in, it causes a 0 in the denominator, which we cannot have. So we look at this, and what we need to determine is, can we factor it? And the answer is yes, we can factor both the top and the bottom here. So that's what I'm going to do. On the top here, I'm going to factor an x out of this. So I've got the limit as x approaches 0. And factor an x out. We get x minus 5 when we factor it out. And on the bottom, I can also factor an x out. And I get x minus 3. And once I have them factored, I can go ahead and cancel out the common x's. So now if I stick 0 in, it doesn't cause a 0 in the denominator. And I'll have 0 minus 5 and 0 minus 3. And that will give me positive 5 over 3. All right, now there are several like this down below. Number 10, where you have to factor to make it work out. Or maybe not. No, this one doesn't cause a 0 in the denominator, so we can just plug in. This one, though, looks like it may very well cause a 0 in the denominator, so you will have to factor. And that, some of these right here, perhaps. And then number 6 is going to be similar to what we did on this one right here. Number 8 also. Let's very quickly do number 9. If this value does not cause a 0 in a denominator, we can just plug it in. So the limit as x approaches negative 8, we just plug it in, is negative 56 minus 2, or negative 58. That's our answer. So we can do that for this one, because negative 2 doesn't cause a 0 in the denominator. This one we have to do like the factoring problem that we just saw. And there may be a few more down below that are, these are different. Okay, so I'm running out of time on this video. Go ahead and try these, and if you need further help, let me know.